So our next lesson is on heaps. Now heaps always make an appearance on the second exam and the final, so it's very important to understand them. And we use them to build priority queues, so that makes them exceptionally special. So the first thing we need to know about heaps is that heaps are complete binary trees. And we're going to just stop right there for a second. So again, this is a drawing of a complete binary tree. If 26 was missing, this would not be a complete binary tree. A complete binary tree, it's perfect. In other words, it's completely filled in and completely balanced for the n-1 level. But on the nth level, we've got it's almost perfect. It's almost all the way filled in, but there's some gaps over here there's some space left over here to the right. Now the big thing here, remember, is that there can't be any gaps from left to right. So if there was if 26 was missing, would not be a complete binary tree. If 36 was missing, but we had 26 through 74, would not be a complete binary tree. If 74 was missing, but we still had these 4 nodes, it would be complete still. It would be complete. Remove 32, also complete. Remove 36, so you remove these 3 guys, also complete. But if we were only missing 76, would not be a complete binary tree. So these 3 nodes. So if we had another node here, also complete. If we had just another node here, but space left over here, not complete. So just kind of want to reiterate that, because what we see on exams is that my questions are often along the lines of, here are a bunch of things, I want you to insert them into heap, and draw it step by step, and the students draw step by step, and I don't get a complete tree. It's always complete. Well, as we'll see, when we add stuff into a heap, it always results in a complete tree. It's necessary for it to be complete. So heaps are pretty essential. I emphasize them pretty heavily. They're about 50 points in the tech timed lab will be going on heaps, but it's actually fairly straightforward. They're not really that hard. It's just that when I see people mess up on heaps, it's because they forget that it's supposed to be a complete binary tree. If you remember that, then it's super easy. All right, so they're not binary search trees, though. They're complete binary trees, so no search property here, right? Notice that the things to the left are bigger, and what's that? The things to the right are bigger too. So with the thing with a heap is that we have 2 types of heap, and we're looking at what's called a min heap over here. Right? And a min heap means that the value of the root is the smallest item in the tree. All right? As you could imagine, a max heap means the biggest value is in the root. We're going to just completely deal with min trees in this chapter. Once we get into sorting and heap sort, we'll look at a max heap. But for right now, we're just going to look at the min heap. Right? So 6 is the smallest thing in the tree. In this tree, right? So in the heap, the smallest thing is the root. Also, every non-empty subtree is a heap. So this property is also recursive, right? Let's take a look at the subtree that starts at 18, right? So 18 is the smallest thing in its tree. 20 is the smallest thing in its tree. 28 is the smallest thing in its subtree, right? This is 18's subtree. So each thing is smaller than everything else in its whole tree. So 6 is the smallest thing here, 29 is the smallest thing in its subtree, 39 is the smallest thing in its subtree, 66 is the smallest thing in its subtree. That's it. That's how we do it. So it's really so fortunately the way it's not too complicated of a data structure, as we're going to see, but that's the premise. So now we will go over insertion, then the next video will go over deletion, and then the video after that we'll go ahead and see. So we're going to look at that and how that's done in theory, like how we actually like how we physically add a node to a tree. And then we'll see how it's actually coded up very briefly. It's kind of actually trivial enough that we don't really need to code it up to show you. So not a very hard concept. They're very cool, even though I kind of made it sound super intense in the beginning.